In Lesson 11.6, we'll be learning about factoring trinomials and other polynomials when dealing with situations where the equations have quite large numbers in them and how we go about factoring and then finding their solutions. So our targets are, we want to be able to factor polynomials, and it won't be just over the integers now. We'll even have some fractions and decimals. Find zeros of polynomials by factoring, which is a continuation of Lesson 11.5, and then apply what's called the fundamental theorem of algebra. So we're asked to factor the polynomial m squared plus 2m minus 6,399, which is a very large number. You'll notice there is no greatest common factor that can be divided out first, nor is this a perfect square trinomial because 6,399 is not a perfect square. So the question is it even factorable? So we've learned to determine that, we find the value of the discriminant. So we need to know the values of a, b, and c. Well, a in this case is 1, the number in front of the m squared. B is 2, the number in front of the m. And c is negative 6,399. So when you find the value of b squared, we'll have b squared, which will be 2 squared, or 4, minus 4 times a times c. And we find that discriminant comes out equal to 25,600. If you take the square root of that on your calculator, you see that it is a perfect square. Its square root is 160. So this is factorable. Now I don't know about you, but I'm not interested in making a list of all the factors of 6,399. So what would be faster would be just to use the quadratic formula and find m, or the possible values of m. So of course we know that formula is x equals opposite of b plus or minus the square root of the discriminant, which we just figured out, all over 2a, which in our case would be 2 times 1, or 2. If I continue to simplify that, I get negative 2 plus or minus 160, all over 2. Well, negative 2 plus 160, then divided by 2, is 79. And negative 2 minus 160, and then divided by 2, is negative 81. That's 79, not 78. So now that we know our solutions, our zeros, then like we learned in Lesson 11.5, we can write our factors. We put an x with each of those zeros, in this case an m with each of those zeros, and then the opposite of the 0 gets put with that m. So the 0 was at positive 79, so I'll have a factor at m minus 79. And again, that's because if I replace the m with 79, that factor would come out equal to 0. I have a 0 at negative 81, so I have a factor at m plus 81, because if I replaced m with negative 81, that would equal 0. So our factored polynomial is m minus 79 times the quantity m plus 81. So in our second example here, we're asked to factor the polynomial 20x squared minus 53x plus 12. And again, you notice there's no greatest common factor. I could use my methods that we learned previously, multiply the 20 by 12 and find factors of 240 that add up to negative 53, which can be done but might be tricky for some of us. So we'll just find the value of the discriminant and see if it's even factorable. A in this case is 20, B is negative 53, and C is 12. So when I find b squared minus 4ac, I find this discriminant is equal to 1,849. That is a perfect square because when I take its square root, it equals 43. So I'll go ahead and factor it using the quadratic formula. x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. That simplifies to 53 plus or minus 43 all over 40. 53 plus 43 is 96, and 96 divided by 40 is 12/5. Now your calculator gave you a decimal, and of course if you're not good at reducing those fractions, you can just hit your math frac button to get the 12/5. 53 minus 43 is 10, and 10 divided by 40 is 1/4. So here's an example where our zeros are fractions, and we want to write the factors, and we want to write them with integer coefficients whenever possible. So here's the trick. We have two zeros, so we're going to have two factors. Each of the zeros is positive, so each of these factors is going to have a negative, because remember we need the opposite in our factors. Each, of course, is going to have an x. But what we can do is take the denominator of each zero and make that the coefficient of the x, and then the opposite of the numerator goes in that binomial. I'll show you why here in a moment. So if I take the denominator of the 0 of 1/4, I'll put that in front of the x, and then the opposite of 1 is -1. It's just a little shortcut that always works when you get fractions for your zeros. Here's why. If you take the 5x minus 12 and you set it equal to 0, to solve for x you'd need to add 12 to both sides and divide by 5. In the end, you get the 0 that you started with. The same would be true if I did that with the 4x minus 1. So again, you take the denominator of the 0 and make it the coefficient of the x, and then the opposite of the numerator goes in that factor with it. So the denominator of the 0 is the coefficient of the x, and the opposite of the numerator goes in that binomial with that. So our factors in this case are 5x minus 12 times the quantity 4x minus 1. If you FOIL that, 5x times 4x is 20x squared. 5x times -1 is -5x. -12 times 4x is -48x. And -5x and -48x add up to -53x. And then -12 times -1 is +12. So it does work.